Alright, this is section 4.3. In 4.3 we take the first and second derivatives, and we find out that when we take the first derivative and we analyze it, we can find out where the original function is increasing and decreasing, and also where it has a local max or min. When you take the second derivative, we can find out its concavity and its inflection points. So, the book and the author do it a longer way. What they do is they obviously take the first derivative and factor it into its smallest factors. And they take each of the factors and draw a column for each one. And now they know that their critical numbers are going to be 0, 2, and negative 1. So when they divide up their number line, right, you get your negative 1, you get your 0, you get your positive 2. And so they check each of these intervals, smaller than -1, between -1 and 0, 0 to 2, and greater than 2. And so if you check a number smaller than negative 1, like negative 2, and plug it in here, 12 times negative 2 is negative 24. Negative 2 minus 2 is negative 4. Negative 2 plus 1 is negative 1. And when they're all multiplied together like they are up here, 3 negatives gives you a negative. And thus you can say the function is decreasing on that interval. Now, from -1 to 0, they plug in like -1/2 into here, and you get negative, negative, positive. But 2 negatives flips back to positive again. And if you plug in 1 in here, you get positive, you get negative, you get positive. And with 1 negative, you still get negative. And then greater than 2, like for 3, you're going to get positive, 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 and all three multiplied together with positives gives you a positive. So you can tell where the function is decreasing and increasing based on these answers in this column here. Now I do it in a simpler way. It's also quicker. You do the same first derivative, setting equal to 0, same finding the critical numbers, same dividing up the number line, but my way of doing it is I just plug in a number in each region into the factored form, and I find the answer for that. I don't find the answer for each individual part. So for -2, that would be negative. A -2 there would be negative. A -2 there would be negative. 3 negatives gives you a negative. -1/2, that's negative. -1/2 there, that's negative. And that's positive. 2 negatives gives you a positive. 1, that's positive, negative, positive. 1 negative gives you negative. And 3, positive, positive, positive gives you positive. So you can state where it's increasing and decreasing on these open intervals. You can also notice that when it goes from minus to plus at -1 and minus to plus at +2, that is a local min. And where it goes from plus to minus, that's the local max. Okay, so they just formalized it that if the first derivative changes from positive to negative at some number, then it has a local max. If it goes from negative to positive, it has a local min. If it goes from positive to positive or negative to negative, it has neither. And they show you how with a local max you're going to have a positive first derivative and negative first derivative. It's going to flip sign. Same thing here. And here, this is positive, and it doesn't have a local maximum. This is negative, and it doesn't have a local min there either. So this is the way I summarize the critical first derivative test. You find your critical numbers by taking the first derivative, factor it, set each factor equal to 0. Divide up your number line that way. Check a test value in each region, and all you care about is the sign of the answer. If you have a plus, that's where it's increasing. If you have a minus, it's where it's decreasing. And when you go plus minus, that's a local max. Minus plus, that's a local min. Minus minus or plus plus is neither. Now notice when you go from plus to minus and you have a local max is a point. So once you find the x value that gives you a local max, you have to plug that into the original function to get the y coordinate for your point, because the local maximum is an actual point. Same thing with local min. Whatever local min you find, whatever x value gives you a local min, you got to plug that into the original function to get your to get the actual point. All right, so here we take the first derivative, and we're only looking from 0 to 2 pi. So when we set this equal to 0 and solve, we get an answer where cosine is -1/2, and that's in these two spots here. And we divide up our number line. It's only from 0 to 2 pi. Divide up our number line, and we check something like pi over 3, pi, and maybe 5 pi over 3. And you plug it into here, and see if you get what sign you get. Well, you end up getting positive, negative, positive. So we know it's increasing from 0 to 2 pi over 3, increasing from 4 pi over 3 to 2 pi, and we know it's decreasing from 2 pi over 3 to 4 pi over 3. We also know we have a local max and a local min at each of these successive points there. Now concavity is the way in which something is increasing or decreasing. It has a certain curve to it. If you look at a cereal bowl that's sitting upright, that is concave up. Anything that has that sort of curve, like a side of a cereal bowl, that's concave up. Now if the bowl is flipped over, upside down, that's concave down. Alright, so if you look at these, this is concave down, this is concave up, this is concave down, concave up, concave up, concave down. Now where the concavity changes, that's an inflection point. So you have an inflection point there, there, there. You don't have one there, but you do have one there. And now you'd have to take those x values and plug them into the original function to complete the y coordinate for your inflection point. So now the second derivative is just like the first. You take the second derivative, set it equal to 0, divide up your number line, and check a test value in each region, and you only care about the sign. And where you have a plus, that's concave up. Where you have a minus, it's concave down. Now there's another aside that the book mentions about the second derivative test. You can actually use the second derivative sometimes to check if something is a max or a min. Now, if you take the first derivative and you get critical numbers, you can actually take the second derivative and take the critical numbers you got from the first derivative, plug them into the second derivative, and if you get a positive, then it's a local min, opposite way you would think. If it's negative, it's a local max. Now, sometimes it will be equal to 0, and that doesn't give you any information at all. Now, personally, I don't know why you'd want to use that technique, because you can just use the first derivative test, and you know where you have a max or a min already. But that is another way that the second derivative test can be used. So here we take the first derivative factor, find our critical numbers 0 and 3, divide up our number line, and we plug them into the most factored form here. So you plug in a minus 1 here, and squared times 4 is positive, minus 1 minus 3 is minus 4, positive times negative is negative. Now plug in a positive 1, that's positive and that's negative, positive times negative is negative. Plug in 4, that's positive and that's positive, so your answer is positive. Now when you take the second derivative and factor, you get 0 and 2 are your critical numbers, and now you plug them into the second derivative, like minus 1 here gives you negative, negative, which is positive. A positive 1 will give you positive and negative, which is negative, and a positive 3 gives you positive, and positive multiplied together gives you positive. So now we can say it's decreasing from minus infinity to 0 and 0 to 3. It's increasing from 3 to infinity. There's no max or min there, but there is a local min at this point here. It's concave up from minus infinity to 0 and 2 to infinity. It's concave down from 0 to 2. And we do have two inflection points at 0 and 2 because the concavity changes. Now sometimes when you're taking a derivative, it's quite complicated how you derive your second derivative. Something like this, when you take the derivative, it's a product rule. So you get the first guy times the derivative of the second. And notice you got to use the chain rule here, because you actually not only bring the exponent out front and subtract 1, you got to take the derivative of what's inside as well. Plus the second half untouched times the derivative of the first, which gives you 2/3 x to the minus 1/3. Now I recommend you write it in fraction form, moving things that have a negative exponent and combining things that you can. And when you do that, you get these two guys here. And when you look at these two, they both have a 3. This one has an x to the 1/3, and that one doesn't, so multiply top and bottom by x to the 1/3. This one has a 6 minus x to the 2/3, and this one doesn't, so you multiply top and bottom by 6 minus x to the 2/3. Now watch what happens when you do that. When you multiply x to the 1/3 times x to the 2/3, you get x to the 3/3. You add the exponents. 3/3 is just 1, so you get minus x to the first. And now here, when you multiply this guy times this, you add the exponents and you get 3/3 for your exponent, which is just 1, so it's 2 times 6 minus x, which is 12 minus 2x. These combine, and you can cancel a 3 with the bottom, and now you've got your first derivative. Now, second derivative is a lot harder. Second derivative, you got the quotient row, so you got the bottom times derivative of the top, which is just -1, minus the top, untouched, times derivative of the bottom. Now, derivative of the bottom, that's the product rule again. So it's first, and then derivative of the second. 2/3 that to the -1/3 times the -1, right? Plus that second guy untouched times derivative of the first, which is 1/3 x to the -2/3. Now, if you clean this up and write things with positive exponents only, this part, you bring the negative out front. And this minus in here, you can distribute the minus there so that it really becomes x minus 4 instead of 4 minus x. It gets rid of that one minus sign that you might have to deal with. Okay, and so now this x to the 1/3 is on top, the 2 is on top, and the minus is on top. The 3 and the 6 minus x are on the bottom. The 6 minus x is on top, the 3 is on the bottom, and so is the x to the 2/3. When it crosses the fraction bar, it becomes a positive 2/3. Now, to clear out your complex fractions, you have to multiply by whatever your denominator is within your fraction. So a 3, a x to the 2/3, and a 6 minus x to the 1/3, and that's exactly what I multiply by, top and bottom. Now when I multiply this guy times this guy, I get a -3, and I get x to the 1/3, x to the 2/3 gives me x to the 3/3, or just x. And 6 minus x to the 2/3 and 6 minus x to the 1/3, when multiplied, gives you 6 minus x to the 3/3, or just 1. Okay, now here, when you multiply this guy times each one of these, the 3 and the 6 minus x cancel, but you just have the top times the x to the 2/3, which is going to give you x to the 3/3, or just x. So you get minus 2x there. Now here, your 3 and your x to the 2/3 go away, so you just have this 6 minus x times this 6 minus x, and that exponent is going to become 3/3, or 1. And now you just expand everything out, and a lot of stuff cancels, and you can even, at the very end, when you have -24 on the top, it cancels with the 3 on the bottom and becomes -8. Right? So now when you divide up your number line by, you have to set each of these factors equal to 0, and here you're going to get 4, 0, and 6. And you divide up the number line, and you check each of these test values with the most factored form of the first derivative, and you get these numbers here. And we know what those mean for local max and local min, as well as increasing and decreasing. The second derivative, when you set it equal to 0, you get 0 and you get 6. Those are your critical numbers. Remember, critical numbers are where it's undefined or equal to 0. Both of these are undefined. So now we take a number like -1, plug it in here and see what sign we get, and plug in a number between 0 and 6 and plug it in here and see what sign we get, and then something greater than 7 and see what sign we get. And so you get minus minus plus, which means it's concave down, and concave up after 6, and you got an inflection point at 6. Now this one, when you take the first derivative and write it as a fraction, you get this guy. Notice e to the 1 over x, no matter what x is never going to be negative. It's just a positive number. But you got a negative out in front, and you got an x squared. So you can basically say that this first derivative is always negative, because x squared is going to give you positive, e to the 1x over x is going to give you positive, and the negative sign is always going to make that answer negative. So we can say it's decreasing over its entire domain. Alright, so the second derivative, when you set it equal to 0 and factor out e to the 1 over x, you get this, and now we can see that we have places at 1/2, and we don't have to worry about 0, because 0 is not a critical number. It's not in your domain. So we check only minus 1/2, and we check on either side, and we get minus plus, and now we know where it's concave up and concave down, and we have an inflection point there. Now they also talk about vertical and horizontal asymptotes. And remember, a vertical asymptote is found where the denominator equals 0, and typically you just have to show the limit as it approaches one side or the other, and it goes off to one of the infinities. The horizontal asymptotes are where you go off to infinity or minus infinity, and generally those are found for rational functions. And if the top is smaller degree than the bottom, it will have a horizontal asymptote. If the top is equal to the same degree as the bottom, it will have an asymptote at y equals the leading coefficient over the leading coefficient. And if the top is 1 degree larger than the bottom, it will have what's called a slant asymptote, which the only way you can find that is by doing long division. And so like I was saying here, you've got for rational functions, your vertical asymptote is where the denominator equals 0. For horizontals, you can look at the three cases. If n is the degree of the top and m is the degree of the bottom, if the bottom's degree is larger, it has a horizontal asymptote at the y-axis. If the bottom and the top are equal, then it's y equals the leading coefficient of the leading term over the leading coefficient of the leading term. And then if the top is 1 degree larger than the bottom, it does not have a horizontal, but it does have a slant, and you have to do long division in order to calculate that one.